You know that feeling when you need to update thousands, maybe even millions of items in a dataset all at once, and your program just grinds to a halt? Well, there's an incredibly clever technique designed to solve that exact problem, turning a painfully slow operation into something that feels almost instant. So let's dive into the elegant world of lazy propagation. So here's our game plan. First, we're going to zero in on the exact problem with range updates. Then we'll introduce the brilliantly lazy solution. After that, we'll pop the hood and see how it actually works, and talk about the huge performance payoff, plus a few common mistakes to avoid. And finally, we'll see where this powerful technique is being used out in the real world. Okay, let's set the stage. Segment trees. They're amazing data structures, right? They're incredibly fast for asking questions about a range of things. But they have this one major weakness, a real Achilles heel, trying to update a whole bunch of elements at the same time. To really get this, let's use a simple analogy. Imagine you've got 10 boxes of candies all lined up. A teacher comes in and says, hey, add 5 candies to every single box from box number 2 all the way to box number 8. Now, the obvious way to do this is to walk over to box 2, open it, add 5 candies. Then go to box 3, open it, add 5. You get the idea. It works, sure, but you can already feel how slow and inefficient that would be if you had a million boxes. And this is the problem in technical terms. With a standard segment tree, asking for information, a query, is super fast. It's logarithmic time, or O log n. Fantastic. But updating a range? That's linear time, O of n. And what that means is the time it takes grows in a straight line with the number of items you're updating. For big data sets, it's a total deal breaker. So how in the world do we fix this? Well, we get lazy. And it turns out, in computer science, being lazy is sometimes the smartest thing you can do. The core idea here is simple. Instead of doing all the work right now, we just don't. We delay it. We put it off until we absolutely have to do it. And that technique is called lazy propagation. The concept is actually really simple, but so powerful. Instead of running around and updating every single element one by one, we just leave a single note, a pending update, on a higher level group that covers the whole range. It's like saying, hey, everything under this big umbrella needs to be updated eventually. We postpone the work. So let's go back to our candy boxes for a second. The slow way, the normal way, is that manual grind. Open box 2, add 5 candies, close it. Open box 3, add 5 candies, close it. And on, and on, and on. It's tedious, it's repetitive, and it's slow. But the lazy way, it's genius. Instead of touching every single box, you just walk up to the group of boxes from 2 to 8, and you slap one big sticky note on them that says +5. That's it. One single action to cover 7 boxes. The real magic is that the candies only get added when someone actually needs to open a specific box. We only do the work. We only unpack that update when we're forced to. All right, so the concept is cool, right? But how does this all actually work under the hood? Let's take a look. And don't worry, we're not going to drown in complicated code here. It really all just boils down to one extra array and 3 simple rules that run the whole show. To pull this off, we need 2 arrays. First, you've got your regular segment tree. We'll call it segtree. This holds all the calculated values, like the sum of a range. But now we're adding a second, parallel array. We'll call it lazy. This is our special array where we're going to keep all of our sticky notes, those pending updates. Now, this is a really important point. A value in this lazy array, say lazy IDX, is 5. It's not for the node itself. It's a promise. It's a note to the future that says, hey, an update of +5 needs to be applied to all the children of this node. It's a command that needs to be passed down. The whole system just runs on these 3 core rules. You have to follow them in this order every single time. First, before you do anything with a node, you have to check, is there a lazy note waiting for me? Second, if there is, you apply that update to your current node's value, and then, this is the propagation part, you push that same update down to its children. You pass the work on. And third, once you've passed the buck, you clean up after yourself and clear the lazy note from the current node. Its job is done. Okay, so we've got the rules, but when we actually start a range update, like add 5 to elements 2 through 8, how does the algorithm actually move through the tree and figure out where to leave these lazy nodes? Well, it all breaks down into 3 pretty simple cases. Case 1 is no overlap. If the node you're looking at has nothing to do with your update range, you just ignore it and go back. Easy. Now case 2, full overlap. This is the secret sauce. If the node's range is completely inside your update range, you update this one node's value, leave a single lazy note for its children, and then you stop. You don't go any deeper. That's what makes it so fast. And finally, there's case 3, partial overlap, where you got to go deeper and run the same logic on the left and right children. So, now that we've seen how it works, let's talk about the results. Because being lazy, it turns out, pays off in a huge, huge way. But it's a technique that you have to be careful with. There are a few common traps that are really easy to fall into. And would you look at that? This right here is the grand prize. Our range update time complexity just plummets from that awful O of n all the way down to O log n. It's now just as fast as our queries. That's not just an improvement, that's a total game changer. It takes an algorithm that was basically unusable and makes it incredibly efficient. But, with great power comes a few ways to trip up. This is an advanced technique, and because you're strategically delaying work, there are a few classic mistakes that everybody makes when they're starting out. So, what are the biggest traps to watch out for? And you'll see these pitfalls mapped directly back to those 3 core rules we talked about. The biggest mistakes are forgetting to check for a lazy update before you use a node's value, forgetting to actually push the work down to the children, and not clearing the lazy value after you've passed it on. And there's one other tricky one, calculating the node's new value incorrectly. Remember, if you add 5 to a range of 10 items, the total sum goes up by 50, not 5. Now, this isn't just some clever puzzle for a computer science class. Lazy propagation is a real workhorse algorithm that powers systems you probably use every single day. So let's take this out of theory and into the real world. Just think about it. When a database needs to update millions of records at once, it needs this kind of crazy efficiency. Or in a video game, imagine applying a poison effect to all enemies in a huge area. That's a range update. Financial systems applying adjustments to a bunch of stock prices. And of course, it's an absolute must-know for competitive programming. So at the end of the day, the takeaway is pretty clear. This technique is what makes efficient range updates even possible. It's a perfect example of how a really clever algorithm can just fundamentally change what you can do with performance. It might be a little advanced, but its power is absolutely undeniable. And that pretty much brings us to the end. We took a slow, clunky linear process and made it exponentially faster, all by just being a little lazy and delaying our work. So the real question I have is for you. Now that you have this tool in your toolbox, a way to update millions of items in the blink of an eye, what kind of complex problems are you going to solve?